Good morning to all of you.
Good morning, sir.
Good morning, sir.
Good morning. Good morning. Is my screen visible?
Yes, sir.
Yes, sir.
Okay. So, are there any questions, doubts?
Hello, sir.
Yeah.
Sir, in classical state bending element,
Yeah.
we suppose if one end is free, then if we put a moment there,
Yeah.
the corresponding degree of freedom which will be affected is del W by del X or del W by del Y. But
Yeah.
in a shear deformable element, the corresponding degree of freedom which is affected is theta.
Yeah.
So can you tell why it is so physically? It is why it is not del W by del X or del W by del Y in that case also.
No, because theta x, because that moment is going with the rotation, and rotation is theta x or theta y in case of first order shear deformation theory. So that is why that will go in the moments would go corresponding to theta x or theta y degrees of freedom, not with del w by del x or del w by del y. Because actual rotation of the normal is given by theta x theta y, not by del w by del x or del w by del y.
Okay, sir, but like that is corresponding to the rotation of normal,
Yeah.
but the plate deflects by del W by del X or del W by del Y, right?
No, it actually the normal rotates. Deflection is given by W, and there would be some del W by del X and del W by del Y corresponding to that. But because moment is going with the actual rotation of the cross section at a particular location, so that actual rotation is going is theta x or theta y. So that is why the moments would go with theta x or theta y, not with del W by del X or del W by del Y. The normal to the deformed surface would be given by del W by del X or del W by del Y, but that's not the actual rotation of the section. Actual rotation of the section is theta x or theta y.
Okay, sir. So movement goes with the rotation of the cross section actually,
Yeah, yeah.
not with rotation of the surface.
Not with the normal to the deformed surface.
Okay, sir.
That's not actually the rotation of the it's the normal to the deformed surface.
Okay,
Yeah. Which is fictitious. It's not the actual. See, if you undeformed configuration, suppose if you draw normal to the middle surface, that will rotate by theta x or theta y, not by del w by del x or del w by del y. So that initial normal is going with theta x or theta y, but you can always have no normal to the deformed middle surface, but that's not the rotation of actual normal drawn in the initial undeformed configuration.
okay. So it goes with the normal which is in the undeformed configuration.
Yeah.
Okay,
So are there any other questions? Okay, then let me start. Is my screen visible?
Yes, sir.
sir. And one more thing I wanted to ask. In
Pardon?
the one more thing, sir, I wanted to ask.
Yeah, okay.
Uh, Sir, you in one of the lectures you wrote about that different hourglass modes like S, and then corresponding to minus X, and then corresponding to minus Y, in
Yeah,
which you were telling about the hourglass control.
yeah.
So in the second rigid body mode, you told that W is proportional to minus Y.
Yeah, because that I said the rotation about x and rotation about y, no? So because I think I would have written in terms of theta x. So theta x is the rotation about y axis. So if the plate is rotating about y axis, it will the corresponding w is going to be in the negative z direction, and that would be if the rotation is unity, the w would be minus x. Similarly, theta y was the rotation about negative x axis. So the rotation about negative x-axis, I don't know whether I wrote minus or plus, but let's say if we write theta x as it is as the rigid body mode, then corresponding W is going to be proportional to uh, no, y coordinate. So that is how I would have written that. So what is your doubt in that?
Sir, that theta x will be proportional to what? W will
No,
be
theta
proportional to
x
minus
is
y or what?
theta x is constant, but
Okay.
corresponding W, if you see, so if we
Okay.
take theta x as unity at all nodes, the constant rotation about y axis, so then when there is a rotation about y axis, the W displacement will be proportional to x coordinate, because it's a rotation about y axis, and it would be for the rotation about positive y axis, the W would be negative, so minus and proportional to x, so minus x.
Okay. When rotation is about theta, when theta y is considered.
Yeah, theta y is rotation about no, this is when we consider theta x. Theta x is the rotation about positive y axis, no?
Okay, sir. Okay.
Yeah. So depending on the rotation, I would have written, I don't remember exactly, but depending on the rotation, whether I wrote about rotation about x axis or rotation about y axis. So depending on if the rotation is about positive x axis, so if it is rotation about positive x axis, I would have written that would be minus theta y, and theta y is constant, and let's say unity, so the W would be proportional to y coordinates, so it would be equal to y. If I would have written that as simply the uh, the theta y, which is rotation about negative x axis, then I would have written minus y for the in in place of for W.
Okay, sir. So for x rotation, you have written minus y, and for y rotation, you have written x.
Yeah, so then so if I have done that way, so rotation about x axis is basically minus theta y, and now if there is a rotation about x axis minus theta y, then corresponding W is going to be proportional to y coordinate. So I would have written in terms of y coordinate, and similarly when there is a rotation about y axis, so that unit rotation will lead to displacement which is proportional to x coordinate.
Okay.
Yeah. Yeah. Any other question? Anybody? Okay. So let me start. So we are continuing with elastoplasticity. Is my screen visible?
Yes, sir.
Yes, it's feasible.
Yes, sir.
Okay. So we are continuing with elastoplasticity. So the last class I had explained about what are the basic concepts involved in the elastoplasticity, and I had also told you that what is the final incremental form of the element level governing equation to find out the incremental displacement. So one of the thing in that was the tangent constitutive matrix. If you recall, no, the element level incremental form of the equation after application of Newton-Raphson method. So we require their CT, the tangent constitutive matrix. So let us look at how to find that out. So today we are going to look at this question: how to find tangent constitutive matrix CT. So this is what we are going to look at. So how to find this tangent constitutive matrix CT, which was coming in the incremental form of the element level governing equation. So first thing, we are going to make use of what is known as consistency condition in plasticity. So the consistency condition So in this, what I am talking about, no, let us say, if I take the where there are two stresses non-zero, say sigma 1 and sigma 2, and we look at the yield surface. So the yield surface is a, let us say this is the initial yield surface and the material is yielding, and then there is a plastic deformation, and then this is the subsequent yield surface. But this is the yield surface, so if the material is undergoing elastoplastic deformation, so F is going to be 0 here also, and in this also F will be equal to 0. Both, the yield function F is going to be 0 because there is a yielding taking place. So yielding, initially yielding or any intermediate step also, the yield function is going to be 0. So the consistency condition is written for loading. Loading means there is a continued elastoplastic deformation. So if loading is there, so you will find that F has to be 0. The yield criteria has to be satisfied. So F will be equal to 0. And if we look at the differential change in the yield function df, so df will also be 0 because no, at the initial, let's say at a particular loading step, there is some elastoplastic deformation is taking place. F is 0, and a slightly increased load also F is going to be 0. So the df will always be 0 for the elastoplastic loading. And if you have unloading, unloading means you have the material has undergone elastoplastic loading, and then you are unloading the material. So you are, when from the state where you are unloading, F is 0, there F is 0, but you will find that df would be actually less than 0, because F would decrease. If it is unloading is going to be elastic, so in that F is going to be less, so df would be negative. Yeah, someone wanted to ask some question.
Sir, when you say like loading, so
Yeah,
initially also the material is in plastic state, right?
yeah, but when I'm saying loading, this is elastoplastic loading.
Okay, so initially also in yielding condition and finally also in yielding condition.
In the yielding condition, yes. So that is what I am referring to as loading. And
Okay.
unloading means initially the it is yielding, but subsequently it is not yielding. It is elastic unloading. So F bit 0, F would be 0, but df would be less than 0. And then you could think of the third possibility, that initially the material is yielding, and then can there be df which is greater than 0. So this is actually not possible. Either you will have loading of the material or unloading of the material. So either this will be the possible state, or this will be the possible state. So this is not possible.
Sir, DF less than 0, is it indicating kinematic hardening? That
No,
is
not
at the,
no. We are not talking. It could be any hardening, kinematic or isotropic hardening, or it could be mixed hardening. But in all cases, if unloading means from a yielding state, and if there is subsequent unloading, then df would be less than 0, for irrespective of what type of hardening
okay,
material is.
okay, sir.
Yeah. So now when we are talking of this tangent constitutive matrix, so we are talking about actually loading a state, because unloading means it would be tangent constitutive matrix would be equal to elastic constitutive matrix. So we are interested in loading. So for the loading, we have already seen that F, which is the yield function, and the yield function is a function of sigma, the plastic work of stresses, or sometimes it might be expressed in terms of equivalent plastic strain also, and the kinematic hardening parameter alpha, or sometimes in the literature it is used as x. So alpha is a back stress. So this is equal to 0, and then df is also 0. So if we look at df, so df can be written in terms of, yes.
So here, like, aren't we considering some case where load is constant or something like that?
If the load is constant, then in rate independent elastoplasticity, there would be no additional deformation. So you will stay at that state.
Okay.
There has to be change in load, no, for the change of the state.
Okay.
Sir.
Yeah.
So how are we saying that DF would be zero in loading? Because it's a load will increase.
Yeah, so but see, always, when the material is yielding, yeah, you have to be always on the yield surface. So the equivalent stress is increasing. Correspondingly, there is a change in the increase in the yield stress of the material, or there is a evolution of the back stress, and therefore F is always zero.
Okay. Because of
So F is going to be always zero. So when you look at the change in F, initially F is zero. In the final next intermediate next immediate state also F is zero. So change in F is zero. That is how we are saying about that.
okay, sir.
Because F is always zero during the loading state. At every loading step, F is when there is a continuous yielding of the material elastoplastic deformation. You are always on F equal to zero. So that is why when you look at change in F, that is zero.
So
So
why
if you
yield
look at,
stress is changing?
yeah, yield stress. If it is isotropic hardening, then yield stress would be changing. If it is kinematic hardening, then back stress alpha would be changing. And if it is mixed hardening, both will change.
So why yield stress will change?
Because of strain hardening. Because when there is the deformation is there in the material, and that deformation, if you look at from the material science point of view, there is the movement of dislocations. And when there is some plastic deformation, dislocations actually get entangled at the grain boundary. So for further plastic deformation, there is a higher stress level which is required for the subsequent yielding, and that is why we are saying that yield stress is changing.
Okay.
So if you look at the df, so since af is a function of sigma, wp and alpha, so it would be in terms of differential changes in sigma, wp and alpha. So we can write df is equal to del f by del sigma transpose into d sigma plus del f by del wp into dwp, due to change in DIF, due to change in WP, and then del F by del alpha into change in alpha. So that is D of alpha. And for the loading case, this is equal to actually 0. So we will be making use of this condition to actually find out the lambda from this condition, and then we will be putting in the incremental stress strain relation to get CT. So we know that d sigma, I had talked about earlier, that d sigma, the incremental stress, can be written as tangent constitutive matrix CT into d epsilon, and this d epsilon is the incremental strain. Okay, and then if you want, so this is what we want, this CT we want to find out. But what we know is that d sigma can be written as actually Ce, the elastic constitutive matrix, into d of epsilon E, and d of epsilon E can be written as in terms of total strain increment. So that can be written as Ce into d of epsilon minus d of epsilon P plastic strain. So if we find out the expression for a plastic strain in terms of d epsilon, then we will get our CT, this tangent constitutive matrix. So this is now for this we are going to make use of what we have already discussed. That is, one is flow rule we have already discussed in the concepts involved in elastoplasticity. So we had said the incremental plastic strain is equal to lambda times gradient of the plastic potential flow function, del q by del sigma, where q is the scalar plastic potential flow function. So I had discussed that. Then if you look at the incremental plastic work, because we also need to look at the expression for WP, we need that. So the incremental plastic, this is no work of stresses and due to plastic deformation. So dwp, the differential change in the plastic work, can be written as sigma xx into d of epsilon xx p sigma yy plus d of epsilon yyp plus sigma zz d of epsilon zzp plus the corresponding contributions from the shear stresses. So tau xy into d of gamma xyp plus tau yz into d of gamma yzp plus tau zx into d of gamma zxp. So now you can see that we can write this incremental plastic work as sigma transpose into d of epsilon p. So that is what we can write. And we know that d of epsilon p is lambda times del q by del sigma. So we can make use of this relationship and can write this as lambda times sigma transpose into del q by del sigma. So dwp can be written like this. Now we have, so in the now we also have this d alpha, so incremental back stress. So that is incremental back stress, that's an internal state variable actually. So we call, we have denoted it by d of alpha. So this is equal to again 6 components: d of alpha xx, d of alpha yy, d of alpha zz, d of alpha xy, d of alpha yz, d of alpha zx. So this is your incremental back stress, and we need a evolution law for this back stress. So the simplest evolution law for the back stress is Prager's rule, although there are more advanced evolution laws for back stress that you can look at in the literature of elastoplasticity. But I am going to look at the simple evolution law for back stress, that is known as Prager's rule. So as per this, as suggested by Prager, that the incremental back stress is proportional to incremental plastic strains. So the Prager's rule, that is actually evolution law for back stress. It says that the incremental back stress is proportional to incremental plastic strains. So that means now if we use a proportionality constant as C, so then we can say d of alpha xx would be C times d of, and this is a uncoupled relationship. So d of epsilon xxp, d of alpha yy would be C into d of epsilon yyp, and d of alpha z would be equal to C into d of epsilon zzp. And similarly, because these alpha xy, these are tensorial components, so we need to use the tensorial component of incremental plastic strain. So d of alpha xy would be C by 2 into d of gamma xyp, where d of gamma xyp is the incremental the engineering shear plastic strain. So similarly, d of alpha yz would be equal to C by 2 into d of gamma yzp, and d of alpha zx will be equal to C by 2 into d of gamma zxp. So this is the back stress, evolution law for the back stress, and this is the simplest in the literature of elastoplasticity. There are more advanced evolution laws for back stress to model more accurately the elastoplastic deformation, and also particularly the cycling loading and so on. So there are other laws. So now if we want to write the same thing in the matrix vector form, so we can say D of alpha vector will be equal to constant C times a matrix here, which is a diagonal matrix. So the diagonal matrix is C. So B, and this side, this vector is D of epsilon xxp, D of epsilon yyp, D of epsilon zzp, D of gamma xyp, D of gamma yzp, D of gamma zxp. So this is in between. Here we have a diagonal matrix. Then we have half, 0 0 0, half and 0, and finally 0 0 0 and half. So now if we call this matrix as L, so you can see that D alpha can be written as C into L. This matrix I am calling as L into D of epsilon P. So we can say that D of alpha as per the Prager's rule would be C into L into D of epsilon P. C is a constant, not a matrix. So that is actually C. And then D of epsilon P is lambda times del Q by del sigma. So we can write the lambda here, and then we will have del Q by del sigma. So this is the evolution law for the back stress alpha. So D of alpha is given by C lambda L into del Q by del sigma. Now for the continued elastoplastic loading, we have already talked about that. So now we have whatever we need in the DF we needed basically DWP. So we have got the expression for DWP. We have written over here the expression for DWP. We need D alpha, so we have got the expression for D alpha over here. So now again we can go back to the consistency condition and get an expression for lambda. That is and we are going to talk about what is the interpretation of lambda. So for continued,
So here we will not find out C,
pardon.
the value of C.
Yeah, C is a material constant. So this has to be determined from the uniaxial test of the material. So if you have got the uniaxial stress strain curve of the material, from that you would deduce C. So subsequently we will talk about how to express C in terms of the material parameters. So C is a constant, lambda is an unknown that has to be determined during the solution process.
Okay, so sir, and what is the physical significance of alpha?
Alpha is, that's what I explained you, the kinematic hardening in my first lecture, no? So because no material, the experimentally what is observed, that if you load the material, let's say first in tension, and then the same and then at some stress level there is a yielding, and then no, after yielding you continue loading up to some point in tension. So that is what I had explained, no, that if you load the material, then there is a yielding. So now let us say this is the initially distress sigma y naught. This is sigma xx and this is epsilon xx. When you unload this material and continue loading in the compression, so the compression, the yielding will start at a load level, stress level, which is smaller than the sigma y naught. So because this whole thing, this is, let us say, some point A. So this total is 2 sigma y naught in case of kinematic hardening material. So if you see this value is going to be less than sigma y naught. So if the material is initially loaded in tension and then in compression, the yielding will take place at a stress magnitude which is lower than the stress at which the yielding is started in tension, that is sigma y naught. And this is so now if you look at the yield function, in yield function we introduce an alpha to actually bring out this effect. So that is translation of a yield surface. The origin of the yield surface changes. So if the initial loading is in tension, then the yield surface translates in the tension side. If the initial loading is in compression, then the yield stress translates in the compression side. So the alpha denotes translation of the yield stress, and in effect it is modeling the material aspect where there is a yield stress is different in tension and compression. So here the initial yielding is taking place at sigma y naught in tension, and in the compression this yield point would be at a stress which is lower than sigma y naught. So this is going to be less than sigma y naught. Okay.
Okay, sir. So like alpha will also change with loading.
Yeah, alpha will also change with loading. Yes, alpha is in terms of plastic strain. Plastic strain is going to change with the loading, so the alpha will also change.
Okay.
So for continued elastoplastic loading, we have two things. That one is F is 0, so F involves sigma Wp and alpha, so this is equal to 0, and the other condition is that df is equal to 0. So df equal to 0, and for the df we have already written the expression that this is del f by del sigma transpose into d sigma. Either you can write d inside or outside, is one and the same thing, plus del f by del wp, del f by del wp into dwp, plus del f by del alpha transpose into d of alpha, and this is also equal to 0 for the continued elastoplastic loading. And now we know that d sigma we want to write, so del f by del sigma is the gradient of yield function with respect to sigma, and then d sigma we have already said that that can be written as c into d epsilon minus d epsilon p, and then now the del f by del wp can into dwp. So dwp we said it can be written as lambda into sigma transpose into del q by del sigma, plus we have this del f by del alpha transpose, and then d alpha we said it is c into lambda into matrix L into del q by del sigma, and this is equal to 0. So now if you see, you also know we have already said where d of alpha p is equal to lambda times del q by del sigma. So this we already know. So now see what we can actually do is, now if you look at this term is in terms of lambda, this term also has lambda, this term also has lambda. The first term, this one will be independent of lambda. So we can solve for lambda basically from this equation. So you can see that lambda from this equation will be equal to del f by del sigma transpose into ce into d of epsilon, and this whole thing divided by no all other terms. So basically this term, when you take it to the right hand side, it would become positive, this term would be negative, this term also will be negative. So we'll have in the denominator del f by del sigma transpose. I'm writing the first term, there is a transpose here, I forgot to write that transpose. So there is a this transpose, please make a note. So del f by del sigma transpose into ce into del q by del sigma, because d of epsilon p is lambda times del q by del sigma. So this is the first term. Other two terms, when they go to the right hand side, they will become negative. So we will have del f by del wp into sigma transpose. That second term I am writing del q by del sigma, and then minus we will have del f by del alpha transpose into c into L, and then into we will have del q by del sigma over there. So this is the expression for lambda we are getting from consistency condition df equal to 0. And let me say that whatever we have now in the denominator here, so let us call that as a. So then you can say lambda is equal to 1 upon a times del f by del sigma transpose into ce into d of epsilon. So what is the purpose over here is that we want to write lambda in terms of the total in no in strain increment d epsilon. D epsilon is the total strain increment which consists of elastic and plastic parts. So we wanted to write lambda in terms of d of epsilon. So that is what we have done. So now if you look at go back to the expression for d sigma, that is ultimately we want to get the relationship between incremental stress and incremental strain. So we know that we have already said that incremental stress d sigma is equal to elastic constitutive matrix into elastic strain, and the elastic strain is total strain minus plastic strain, plastic strain tensor. So that is, you can write actually this d sigma here as ce into this d epsilon you keep as it is, and minus this is lambda times del q by del sigma. And then now we have got the expression for lambda. So we can say that d sigma is equal to ce into d epsilon. And then now we can put the value of lambda. So let me write minus del q by del sigma, and then the expression for lambda, which is 1 upon a. So 1 upon a, let me write over here. So this is del q by del sigma, and then the expression for no lambda. And so 1 upon a I have already written. So what we are left with is del f by del sigma transpose into ce into d of epsilon. So this is what we have got. So now you can see that d of sigma, if we take d of epsilon common and take everything inside, so we can write d of sigma as matrix ce. So if you take the c inside and d epsilon take common on the right hand side, so we will have c, then minus 1 upon a, then this c is in the multiplication, and then we have del q by del sigma into del f by del sigma transpose, and then we have this c again over here, and then this bracket closes, and then you have here d of epsilon. So now see, we have the relationship between the incremental stress d sigma and the incremental strain total strain d epsilon. In between whatever matrix is coming, that we call as constitutive matrix. So we write this relationship as basically ct into d of epsilon, and where ct is equal to the tangent constitutive matrix. Ct is tangent constitutive matrix is equal to ce. Ce, superscript e stands for elastic here. So that's the elastic constitutive matrix. So as if the material is linear elastic. So for that, whatever constitutive matrix you have, that is ce minus 1 upon a into you have ce into del q by del sigma into del f by del sigma transpose into ce. So this is your ct, the tangent constitutive matrix. Now we would have the various when we solve the entire problem starting from zero loading, and then we increase the load, so we will have various stages of loading. So first we will have no elastic region where there is no yielding of the material, it is purely undergoing elastic deformation. So in that case, ct would be simply equal to ce, it would be equal to the elastic constitutive matrix. Now for the elastoplastic region, we have already elastoplastic region loading, then we know the ct expression, we have derived this entire this ce minus 1 upon a into ce into del q by del sigma del f by del sigma transpose into CE. So this is CT in that case, and when there is a elastic unloading, the first is elastic actually loading, and then there between incremental stress and strain will be
Screen
equal to the elastic constitutive matrix. Hello? Yes?
screen
Yeah, any
problem, but
problem?
it's okay. It's okay now.
Okay. So now this is the CT, the tangent constitutive matrix which relate the incremental stress and strain, will be given by CE or this expression or CE, depending on what state of loading you are, whether it is elastic loading, elastoplastic loading, or elastic unloading. So this will be the tangent constitutive matrix. Now we look at the more we want to look at the interpretation of this term lambda which we have, the proportionality constant in the flow rule, how is it related to the incremental strains, and we also would define the the equivalent incremental plastic strain. So those are some of the things we want to look at it. So now the first thing is, let us consider the one Mises yield criterion. So if we are considering one Mises yield criterion, and one Mises yield criterion and then associative flow rule. So one Mises yield criterion, associative flow rule, and yeah, so let's first talk about this. So now we know the yield function f, if you look at, and also let me say that there is no kinematic hardening, only there is isotropic hardening. So let me also say isotropic hardening. So one Mises yield criterion, associative flow rule, and isotropic hardening. So in that AF, because there is no kinematic hardening, so alpha would be 0. Isotropic hardening means alpha is going to be a null vector. When we say isotropic hardening, flow associative flow rule means Q is actually equal to F, and of course one Mises yield criterion. So for this, if you look at your F is going to be it's equal, in terms of equivalent stress. It is also known as J2 flow theory. So equivalent stress would be, I am writing the final expression. I expect you to derive the expression for one Mises stress. So you can calculate the CRS in the octahedral plane and then equate it to the corresponding uniaxial octahedral shear stress and get the expression for equivalent stress. So that equivalent stress is, I'm not going into that derivation. So it's a sigma xx square plus sigma yy square plus sigma zz square minus sigma xx into sigma yy minus sigma yy into sigma zz minus sigma zz into sigma xx, and plus we have 3 times tau xy square plus tau yz square plus tau zx square. So this is equivalent stress minus that minus, now this term is outside the square root sign, so that sigma y is the yield stress is equal to 0. So this is the one Mises yield criterion. So now that now when the material is yielding, of course with the continued elastoplastic deformation, this sigma y is also going to change with the plastic strain, and of course the components of the stresses will have changed. And as I said, no, because it is associative flow rule. So if you look at the plastic strain, so d of epsilon p would be lambda times del q by del sigma, which will be, because q is equal to f, so this would be del f by del sigma. Now if we want to look at the components of the plastic strain, so the plastic strain components are proportional to del f by del sigma, so that is also known as the normality rule. So if you look at del f by del sigma xx, because that is the components of del f by del sigma. So one is del f by del sigma xx. Now if you look at the del f by del sigma xx, you are going to, this is your f, and you are going to differentiate this with respect to x. So first you differentiate with respect to this, whatever square root sign is there. So we will get half and 1 divided by square root of, you know, the sigma xx square plus sigma yy square, so on, plus then 3 times tau xy square plus tau yz square plus tau zx square. So this is what you will get here, and then in the numerator derivative of whatever is there inside, and see sigma y, the yield stress is not a explicit function of sigma xx, so that term will not come over here. So then the derivative of the quantity which is inside the square root sign with respect to x, so that this term will give you twice of sigma xx, then this will give you minus sigma yy, and then this will give you minus sigma zz. So this is what you get, and so this is del f by del sigma xx. If you look at, because f is equal to 0, so whatever we have now inside this square root sign, that is actually equal to sigma y. So you can write now this whole term as twice of sigma xx minus sigma yy minus sigma zz divided by, no, that 2 is inside, no, not outside the, so that is twice of sigma xx minus sigma yy minus sigma zz divided by 2 into sigma y. Sigma y is the yield stress here, no, keep in mind that this is yield stress of the material, and which is not constant, it changes with the plastic strain. And now we want to write this in terms of deviatoric stress components. So you can actually write this as multiply and divide by 3. So you can then write it as 3 into sigma xx d deviatoric stress divided by 2 sigma y, where sigma xx d deviatoric stress is equal to twice of sigma xx minus sigma yy minus sigma zz divided by 3. So this is sigma xx minus mean stress, sigma xx minus sigma xx plus sigma yy plus sigma zz by 3. So you get actually, you know, this expression, and this is a component of deviatoric stress. So similarly, if you look at the, hello, am I audible?
Yes, sir.
Hello.
You're audible, sir.
Okay. So now similarly, if you look at del f by del sigma yy, so you will find similarly this would be twice of sigma yy minus sigma zz minus sigma xx divided by twice of sigma y, which can be written as actually 3 by 2 times sigma yyd upon sigma y, and where sigma similarly, no, where sigma yyd is twice of sigma yy minus sigma zz minus sigma xx divided by 3. So that's also the deviatoric stress component. So same way, if you look at del f by del sigma zz, this will be equal to 3 by 2 into sigma zz upon sigma y. So that is how you can write the derivatives of the yield function f with respect to sigma xx, sigma yy, and sigma zz. Now similarly, if you look at del f by del tau xy, we'll have to look at all the component, all the 6 components. So again, no, when we have this 1 upon 2 sigma y, and then the derivative of this quantity which is inside the square root sign with respect to tau xy. So that's only this term. So it will give you 6 tau xy. So we will have here 6 into tau xy. So that can be written as 3 tau xy divided by sigma y. And the shear components of deviatoric stress are same as the stress tensor itself. So this can also be written as tau xyd upon sigma y, where no, where tau where tau xyd is nothing but equal to tau xy itself. So same way you will have del f by del tau yz would be equal to uh, 3 times tau yzd upon sigma y, and del f by del tau zx will be equal to 3 times tau zxd upon sigma y. So now if you look at the incremental, we are using the associative flow rule. So now if you look at the incremental plastic strains, incremental plastic strains. So we know that d of epsilon xxp is lambda times del f by del sigma xx. For associative flow rule, q is equal to f. So we are using del f by del sigma xx, and del f by del sigma xx is already 3 sigma y by d upon 2 sigma y. So we can write it as 3 lambda upon 2 into sigma y y d upon sigma y. Similarly, you can write epsilon yyp will be lambda times del f by del sigma yy. That would be 3 lambda by 2 into sigma, sorry, this is sigma xx. This is xx, not y. Similar, this will be yyd upon sigma y. And then you will have d epsilon zz. Similarly would be lambda into del f by del sigma zz. That would be 3 lambda upon 2 into sigma zz upon sigma y. And so similarly you can look at the shear components of plastic strain. So d gamma xy is lambda times del f by del tau xy, and that is equal to 3 lambda into tau xyd upon sigma y. And same we know the other two. So similarly you can write gamma yzp will be equal to 3 lambda tau yzd upon sigma y, and d of gamma zxp will be equal to 3 lambda into tau zx d upon sigma y. So you can write like this. Now let's see for this 1 Mises yield criterion, associative flow rule, and isotropic hardening. What about the volumetric plastic strain? So let me look at the incremental volumetric plastic strain. We are of course considering the small deformation case. So d of epsilon vp, v for volumetric and p for the plastic, and d is for the increment. So this will actually be d of epsilon xxp plus d of epsilon yyp plus d of epsilon zzp. And now if you substitute the d expressions for d of epsilon xxp, d of epsilon yyp, and d of epsilon zzp, so you can take 3 lambda upon 2 sigma y common, and then what you will have inside is sigma xxd plus sigma yyd plus sigma zzd. And if you look at the sum of these three, sigma xxd plus sigma yyd plus sigma zd, as per the definition, you will get that as 0. So this is 2 sigma y into 0. So the conclusion is that d of epsilon vp is equal to actually 0. So what it means is that the incremental volumetric plastic strain is actually 0. So we can say that the plastic deformation is volume conserving. So the conclusion from this is that plastic deformation is volume conserving because the volumetric strain is actually 0. So next is we want to define another quantity which is known as equivalent incremental plastic strain. So that's the another definition we want to give, and then we want to interpret lambda also in the process. So next is equivalent incremental. So these are all the concepts in plasticity, in plastic strain. And let me denote it by d of epsilon eq for equivalent and p. So when we define this quantity, we have two requirements. One is that d of epsilon equivalent p should be equal to d of epsilon xxp in uniaxial loading. So we want to define it in such a way that for the uniaxial loading case, the equivalent d epsilon equivalent p is equal to d of epsilon xxp in uniaxial loading. And the second condition is that the incremental plastic work of stresses, the dwp, incremental plastic work of stresses should be equal to product of equivalent stress and equivalent incremental plastic strain. So these are the two things which should be satisfied by the definition of this d epsilon equivalent p. So how we define is, we define this d of epsilon equivalent p in terms of the components of plastic strain. So it is defined as square root of, so the entire quantity what I'm going to write is inside the square root sign. So that is 2 by 3 into d of epsilon xx p square plus d of epsilon yy p square plus d of epsilon zz p square. So that is 2/3, and then plus we'll have 1 by 3 of d of gamma xy p square, because we have engineering shear strengths here. So you will see that the half and 2 get cancelled. So we will have plus there d of gamma yz p square plus d of gamma zx p square, and that bracket closed. So this is what is the definition of equivalent incremental plastic strain. And now if we want to check whether it satisfies the two criteria we talked about or not, so let's look at that. So now let us look at the uniaxial loading. Uniaxial loading, yeah.
So here the equivalent incremental, that the
Yeah.
strain which you are defining,
Yeah,
plastic strain. So is it
yeah,
defined like in a similar way as we define the equivalent stress?
yeah, it is somewhat similar, yes. But here, because we have to talk of because I am using here the engineering shear strain, so that factor in one it is 2 by 3, with the engineering shear strength this factor is 1 by 3. So that's the difference. But it is similar to that. It's not exactly same, but similar to that. So now if you look at the uniaxial loading, so uniaxial loading means we take as we do the uniaxial, say, tensile test, so we have sigma xx over here, sigma xx over here, and then we have the uniaxial stress strain curve, sigma xx and epsilon xx. There is initial elastic loading and then elastoplastic loading, and this is happening at sigma y naught initially the stress, and then the stress is increasing. So for the uniaxial loading, if you'll see that df epsilon xxp would be some value, but if you look at the sigma yy and sigma zz are 0, tau xy no, in uniaxial loading only non-zero component of stress is sigma xx. Sigma yy, sigma zz, tau xy, tau yz and tau zx, all of them are 0. So, but if you look at the strain, so we will have d of epsilon YYP, because no, the plastic deformation is volume conserving, so the Poisson's ratio is 0.5. So this would be minus 0.5 into d of epsilon XXP, and similarly d of epsilon ZZP would be equal to minus 0.5 into d of epsilon XXP, and the other plastic strain components, shear components, would be 0. So d of gamma XYP equal to d of gamma YZP plus d of gamma ZXP. These will be equal to 0. So now for this case, if you calculate this d of epsilon equivalent P, which is 2/3 of it is going to be d of epsilon XXP whole square plus d of epsilon YYP whole square. So that will give you 1 by 4 d of epsilon XXP whole square and plus 1 by 4 d of epsilon XXP whole square. So you will find when you simplify this, you will get d of epsilon equivalent P is equal to d of sigma XXP. So that's the first condition we said, that whatever we define as the equivalent plastic strain, that should be equal to d of epsilon XXP for the uniaxial loading case. And then we also have to look at the other condition, that the incremental plastic work should be expressed in terms of the equivalent incremental equivalent plastic strain and equivalent stress. So before we can do that, let's interpret the lambda and what is the relationship between lambda and d epsilon equivalent P, because we have used lambda, and lambda was used in the flow rule, that is d of epsilon P is equal to lambda times del q by del sigma, and for the associative flow rule q is equal to f. So that we have already said. So relation between lambda and d of epsilon equivalent P. So if we want to look at that, so now what we have to do is, we already know the expressions for all the the plastic strains for the one Mises yield criterion and associative flow rule, that this is 3 lambda upon 2 sigma y into sigma xxd, and other components we have already said. So now if we go for this, if we want to substitute this, so we have to put d of epsilon equivalent P, and in the definition we want to put it here. So we will have 2 by 3, and then in all three d of epsilon XXP, YYP and ZZP, we'll have 3 lambda upon 2 sigma y common, so its square would be 9 lambda square upon 4 sigma y square. So this will be common, and then inside you will get sigma XXD square plus sigma YYD square plus sigma ZZD square. So this is what you will get, and inside the square root sign itself you will have plus, and then 1 upon 3, and in all the here we have 9 lambda upon sigma y, so 9 lambda square upon sigma y square you will have, and then inside the bracket you are going to have tau xy d square plus tau yz d square plus tau zx d square. So now if you simplify this, you have to put the values of sigma xxd in this, sigma yyd in this, sigma zzd in this, and of course tau xyd is tau xy, tau yzd is tau yz, and tau zxd is tau zx. So if you put all the values and simplify, you must do that. No, at least no, when you are learning it for the first time, you must cross check that. So this comes as lambda square upon sigma y square, and inside after the simplification you will get sigma xx square plus sigma yy square plus sigma zz square minus sigma xx into sigma yy minus sigma yy into sigma zz minus sigma zz into sigma xx plus 3 times tau xy. So 3 times tau xy square plus tau yz square plus tau zx square. So this is what you get, and see what you have is, finally you can say this is nothing but this quantity is sigma y square. So this is ultimately, you can say that d epsilon equivalent p is nothing but actually lambda. So yeah, so this is no, you can, so finally you can say the plastic multiplier lambda in the flow rule is actually equivalent incremental plastic strain as we see here. So lambda is nothing but equivalent incremental plastic strain d epsilon eqp. No, so that's the definition of lambda. Then the last thing I want to discuss another couple of minutes is the incremental plastic work of stresses. Incremental plastic work of stresses. So by definition we know that d of wp is equal to sigma transpose into d of epsilon p. We have already talked about this. And now if you substitute the values of, no, so you can say now this is nothing but sigma xx into d of epsilon xxp plus sigma yy into d of epsilon yyp plus sigma zz into d of epsilon zzp plus we have no the other terms like tau xy into d of gamma xyp and so on, the two more terms we have already uh, actually discussed that. We have written that expression. So now what you can do is if you substitute the values of d of epsilon xxp, d of epsilon yyp and d of epsilon zzp and so on, based on the flow rule for the one Mises yield criterion and associative flow rule. So we would see that this is sigma xx 3 lambda upon 2 sigma y into sigma xx d plus sigma yy 3 lambda upon 2 sigma 2 sigma y into sigma yyd and so on, no. So like that, no, you can write all the terms plus sigma zz into 3 lambda upon 2 sigma y into sigma zzd plus tau xy into 3 lambda upon sigma y into tau xyd, which is tau xy plus tau yz into 3 lambda upon 2 sigma, no, not 2, upon sigma y into tau yz and plus tau zx into 3 lambda upon sigma y into tau zx. So if you now again put the values of sigma xxd, sigma yyd, sigma zzd in this and simplify, you would be able to write, no, this dw of p. The intermediary steps I leave it to you to try out. So you will find that this would be lambda into sigma y, and so you can say that d of wp is equal to see lambda we have already shown that lambda is equal to d of epsilon equivalent p. So we can say that this is equal to d of epsilon equivalent p into sigma y. Sigma y is the yield stress of the material. You can also write it as equivalent stress. So this is sigma equivalent p into sigma no, d epsilon equivalent p into sigma equivalent. So the way we have defined the equivalent plastic strain, which is equal to lambda, so we get the incremental plastic work of stresses at the epsilon equivalent p into sigma equivalent. So I think this is where I want to stop today, and if you have any doubts and questions you can ask. Yes, so are there any questions, doubts?
Sir, I have one doubt from previous lectures, sir.
Yeah, okay, you can ask.
Sir, actually, I was trying to make the global matrices, like just for practice from element matrix. So, sir, I
uh,
got
for,
one doubt
for
actually.
which for which problem, for which problem?
Sir, like for the exam, sir. Like I was
No,
reading the notes. Sir, like for CPT, sir, let us assume this is for CPT.
okay,
Okay. So,
yeah,
sir, in that case, like we were writing W as like sum of different powers of X and Y, right?
yeah, yeah,
And later on, we found out KE, like elemental K matrix.
yeah.
Uh, Sir, so when we will like find like while formulating the KE matrix for second, third, and fourth, Sir, will we be using the old matrix only, like old KE matrix only, or will
Yeah,
it
yeah,
be
but
dependent on
actually,
SY coordinate?
as long as the element size is same and the properties are no Young's modulus, Poisson's ratio, thickness is same for all the elements, so you can use the same KE. It would be
Okay.
same for all the elements.
Yes,
Be with local coordinate at the first node of the element.
okay. So, sir, like when we wrote W del W by del X del W by del Y, we were writing actually on the basis of local coordinates, right?
Yeah,
Not
right,
on the
right.
basis of
Yeah,
global.
local for the classical plate. What we did was with the local x and y coordinates.
Okay, sir. So that was the doubt only. Actually, I was
Yeah,
thinking that
local.
was it global or
Yeah,
okay, sir.
it's local. Yeah, if you use the global coordinates, so then for different elements, the expressions for say functions would be different. Although finally the stiffness matrix would be same in terms of the length of the element along x and y, if it is and yeah, Young's modulus Poisson's ratio, thickness. But
Yes.
the expressions for the shape functions would be different if you use the global coordinates, because the global coordinates for different nodes of a particular element are going to be different.
Okay. So, sir, like till now, whatever we have done, like in all the cases, we have assumed the local coordinates only
Yeah,
while
right.
forming the KE.
Yeah,
Okay.
see, in case of isoparametric formulation, we need not use the local coordinate. We can use the global xy coordinate and do the formulation. So that is still a straightforward. The expressions are going to be same
Okay.
for the isoparametric natural coordinate formulation.
Okay, sir.
Yeah.
Sir, in this regard, I have also a question. Sir,
Yeah.
shape function for isoparametric element is same for every element,
Yeah, yeah. Because
but
each element in the physical coordinate space is mapped to the same square in the natural coordinate space.
NHL coordinate. But
Yeah,
when we are using the general elements like quadrilateral element, then
yeah,
we like four noded 3 degree of freedom element. Then
yeah,
there will be 12 shape functions.
yeah.
Then will this shape function will change to every element to every element?
If you write these shape functions in terms of local xy coordinate with origin, let's say at the left bottom node of each element, then the shape functions would be same. But if you use global coordinate system, that means the global coordinates of different nodes of different elements are going to be different. In that case, the expressions for the shape functions would be different for different
Okay,
elements.
so let's
But if
assume for my case, I am assuming that it is a square, that is A and B all is one, and
yeah,
according to that I get the 12 shape functions.
yeah,
Then I put that element to all the meshes. So
yeah,
shape function should be same, right?
yeah. So in that case, what you are using is for each element you are using local xy coordinate, no, with origin at
Yes.
top bottom left node, no, that you are taking as origin. So as long as you do that, the element level governing equation for all the elements would be same, provided other properties are independent of xy.
Okay, sir. Thank you.
Yeah,
Sir,
yeah,
sir,
Then,
if
sir,
you
in
get
that
same
case,
problem,
whatever, hello,
yeah.
sir, in that case, then whatever the stiffness matrix we get, is it same as we get from the global system?
Yeah, that would be same. Final expression for stiffness matrix, load vector. If only condition I'm putting, if the all properties E, Young's modulus, Poisson's ratio, thickness, length of the element along x, y, and y, if they are same, and Q, if they are same for all the elements, then you will find ultimately whether you use the local coordinate system for each element or global coordinate system for each element, the element level stiffness matrix and load vector will be, external load vector will be same for all the elements.
Okay, sir. Thank you.
Yeah. Any other question, anybody?
Sir,
Yeah,
sir, the two elements we studied, one is the shear deformable and another is the classical plate
yeah,
bending element.
yeah, yeah.
The shear deformable can sustain twisting moment, right?
Say again.
The shear deformable plate
Yeah,
using FEM.
twisting. Yeah, at edges we have separately. In the boundary conditions and the internal load vector, we have twisting moment mxy. Yeah, mns or mxy.
But not in classical.
Not in classical. In classical, MNS is clubbed with Q and Z, and denoted as V and Z. If you remember V and or V and Z, I would have denoted it.
Okay, so the twisting moment gets carried on to the normal moment
That's-
and the shear
yeah,
moments.
yeah,
Okay.
Hello, sir.
yeah.
Sir, as you said, sir, if we apply local coordinate or global coordinate for both the
Hmm.
cases, it will be same. But the derivation will be something. What we are doing, area integration with respect to area. In
Yeah,
local coordinate, it always be 0 to 1
yeah. 0 to 1 or 0 to A and 0 to B.
to be. But
Yeah,
in global coordinate, it will be 1 to 2 or 0 to 1 like that. It will come.
yeah. Correct.
Then
Yeah,
how
correct.
then how it will be same? Finally, how it will be if we are using local coordinate and global coordinate, both will be same. How it will be same?
Yeah,
That
it will be
one.
same. No, the integration limits are different, but when you look at the expressions, the shape function also are going to be different. But when you take the derivatives and integrate after multiplication, that result will be same, because the shape functions are also different, no, for global coordinate system.
That
So
that
there,
that is that is the only confusion, sir. Because in A matrix, all are represented by x1 and y coordinates.
yeah,
I thought we local we can use local coordinate or not. So
you
only
can use local coordinate, you can use global coordinate also, but the global coordinate formulation will be much more complex.
yes,
So
understood.
it is easier to use the local coordinate system. The formulation becomes simpler. The results are same.
Okay, okay, sir. Okay, thank you, sir.
Yeah. Okay. Yeah. Any other question? Anybody? Hello. Any other question? So if there are no questions, I am stopping here. Thank you all for your attention.